Hi friends, in the last video by saying that bar magnet is equivalent to a solenoid, we have derived this formula. You remember? Since we have completed this chapter electrostatics, we already know that axial field for a short electrical dipole is this one, 2 p pi 4 pi epsilon naught r cube where p is dipole. Now, what is the difference between these two formulas? Just here you have p and here you have m, the magnetic moment, and here you have 1 by epsilon naught and here you have mu naught as constant. Okay, does this thing work for all these formulas? Yes, it does. Wherever you have P, write M, and wherever you have 1 by epsilon naught, replace it with mu naught, and wherever you have electric field E, you write magnetic field B. That's it. You can write all these formulas just by taking a look at these formulas, these set of formulas. Okay, this particular analogy has reduced us a great deal of work because you don't have to derive all these formulas again now. Okay, let's move forward. Gauss law. The net magnetic flux through any closed surface is zero. In mathematical form, I can write this as B dot ds is nothing but zero, where ds is the area. Okay, this is because you don't have any isolated magnetic poles. We discussed before, right, that magnetic monopoles do not exist, and that is why you have a zero here. In electrostatics, what happened in Gauss law? Have a positive charge where we had field lines emitting from emitting out of this positive charge, right? And those field lines were taken by negative charges. But here you don't have this magnetic monopoles, so you don't have anything called as sources of magnetic field lines, or you don't even have sinks of magnetic field lines. They are continuous loops, and that is why you have a zero here. Okay, let us check this. Take any closed surface. I'll take this one. Two lines are entering, two lines are going out. It is zero. Take this one. I don't know how many, but these lines are leaving out of the surface right here. And note that they are entering here. So net number of lines entering is equal to net number of lines going out. Take any this surface wherever you take it. One thing is for sure, the total number of lines entering will be equal to number of lines going out because they are continuous loops. So that proves it. Let's move forward. And note that they may appear like loops to you, these things, but actually they are closed surfaces. Because it is a two-dimensional screen, I'm not able to show it completely. Just try to imagine this in 3D. The figure which you see, it will be the same on all the planes that pass through the axis of this magnet. I mean, these field lines come out in all directions. Just try to imagine three-dimensional space. However, let's move forward. Earth and magnetism. Earth is a big magnet, you know that, and Earth has its own magnetic field. In fact, this is the field which points the magnetic needle inside the compass and show the direction to the sailors, say, in the sea. And not only that, this magnetic field of Earth is one of the key features that has made life possible on Earth. Sun emits some charged particles, and they are very harmful. And when they approach the Earth, this magnetic field deflects them, and hence we are protected. It acts something like a shield. Had this magnetic field been not there, Earth would have been barren, believe me. And of course, Jupiter is a planet which has a magnetic field which is 10 times stronger than that of Earth's, but I'm least bothered about it. Let's get into the topic. This Earth's magnetic field is thought to arise because of electrical currents that are produced by motion of metallic fluids like iron or nickel inside the outer core of Earth, and this is known as dynamo effect. Let's get some detailed idea about the magnetic field lines of Earth. Say this is the North Pole, geometric North Pole, and this is the geometric South Pole. What happens here is the magnetic field lines don't come out and go in out of these poles, but there is something called as magnetic north pole. This one it is. And there is something called as magnetic south pole. They are different from geometric poles. And this line which joins these two, it is inclined to the what? To the actual axis of rotation of Earth. This angle is is 11.3 degrees currently. Why am I saying currently? Because it changes with time. It may tilt by 2 or 3 degrees more in maybe a couple of centuries. God knows that. Now, this magnetic north pole is uh, is at location 79.74 degrees north. This is the latitude, and 71.8 degrees west. This is the longitude. And and you have magnetic south pole at 79.74 degrees south and 108.22 degree east. This magnetic north pole is somewhere in North Canada, and this is somewhere in Antarctica. Observe one thing here. You know that magnetic field lines come out of North Pole, right? But here, this is the way. They go into the magnetic North Pole and come out of the magnetic South Pole. Of course, they are continuous loops. You have something like this. So, the magnetic North Pole is behaving like the South Pole of bar magnet, which is placed inside the Earth or something like that. Okay. I personally feel that it would have been better if they named this one as magnetic North Pole and this one as magnetic South Pole. But I read somewhere that this convention arose because the magnetic north was the direction to which North Pole of the magnetic needle pointed, and so the North Pole of magnetic needle was named as North Seeking Pole. But actually, the North Magnetic Pole behaves like a South Pole of the bar magnet placed inside the Earth. Okay, actually there is no magnet placed inside that. As I discussed before, it arises due to the electrical currents and some stuff like that. In the last video, I said that when a bar magnet is suspended freely, it approximately points to the geometric north pole. Now you understood why it points approximately, because it actually points the magnetic north pole. So, provided you are in this region, that is, if you are not too close to the poles, it really doesn't matter much. Let's move forward. Magnetic declination or simply declination. You know that Earth has a magnetic field, right? And it's not always parallel to the ground. It's not always horizontal. So say this is the magnetic field of Earth. I can resolve this into two components. One is horizontal component and other is say some vertical component. And now this angle is known as dip, or I can write it as tan inverse of this vertical component by horizontal component of Earth's magnetic field. This is known as dip. So what can I write? I can write He as B cos I, where I is the dip, and I can also write Ze as B sin I. You got what is dip? Now, what is magnetic declination? This is a compass, say magnetic compass. You know that it doesn't point exactly to the geometric north pole. Just now we discussed it. So it points to the magnetic north pole. But there is something called as geographic north pole. So this angle between these lines joining the compass needle and both these poles, magnetic as well as geometric, this angle is known as magnetic declination. Hope everything is clear till now. Let's solve a small problem. The horizontal component of Earth's magnetic field is given as 0.26 Gauss, and dip angle is given as 60 degrees. So I have to find the actual magnetic field. It's very simple. Cos 60 is what? Is He by B, and cos 60 is 1 by 2. and I have horizontal component as 0.26 into 10 power minus 4 Tesla. From this you can get the magnetic field. Let me write it in Gauss only. 0.52 Gauss, or 5.2 into 10 power minus 5 Tesla. Both are the same. Hope everything is clear till now, and keep watching. Bye.